In the previous class, we started discussing about fundamentals of convective heat transfer, its various steps, and the basic governing equations for the convective heat transfer. Because we cannot separate convective heat of transfer mode of heat transfer by convection from the fluid dynamics. So it is necessary to study the laws of motion, like law of conservation of mass and momentum equation, law of conservation of momentum and energy equations. While discussing about these equations, these are called as a basic equations of motion. From this, what we have discussed in the earlier class is nothing but law of conservation of mass. We have discussed about it now, and we have described the momentum equation for the basic momentum equation or skeleton of the momentum equation initially, and we could not able to cover this in the earlier class, in the previous class. Now I'll be discussing about the momentum equation once again, and I'll try to derive this momentum equation today. Okay. See, the momentum equation is derived from second law of motion. It is already yesterday I discussed about it. Now today I'll try to discuss this again once again in a brief note, and again I'll go to that derivation part to complete it. Okay. Now, if you see the momentum equation here, as I said, the momentum equation is derived from Newton's laws of motion. What it says is nothing but sum of all forces acting with the control volume, sum of all forces acting in control volume must equal to the rate of increase of the fluid momentum within the control volume, right? Sum of all forces acting on the control volume must equal to the rate of increase of the momentum of fluid within the control volume. Or in other words, also the mass times the acceleration we do consider in this momentum equation are going to be body forces and surface forces. And body forces are proportional to the volume, and which acts on the fluid particle from an external force field such as gravitational, electric, and magnetic, etc. magnetic forces, right? So which is proportional to the volume. Body forces are proportional to the volume, and which acts on the fluid particle from an external force field, such as external force field could be gravitational, electric, and magnetic field. Similarly, surface forces are resulted from the from such as static pressure and viscous stresses. It is proportional to the area, right? So this we have discussed in the class. And again, now and again, if I combine these are all those things, the momentum equation could be mass into acceleration in direction j is equals to surface force action direction j, and again body forces in direction j. This we have discussed. So now, as first law of conservation of mass or continuity equation derived for two-dimensional. This also I am deriving for a two-dimensional, and it is a steady and incompressible flow. This also we have discussed there also. Now this is also I am same case I am taking here. Means what? The momentum equation deriving for two-dimensional steady and incompressible flow with a constant properties in Cartesian coordinates, like j is equals to x. J direction is x y. J direction j is x and y components it's having. Okay, will give two independent momentum equations x and y. One is for x and another for y direction, right? And mass, you know that if density is given to you, density into volume is equals to mass. Therefore, rho into dx into dy, and dz is equals to unit 1. Therefore, dx into dy into 1 is mass. And acceleration is nothing but rate of change of velocity. Therefore, total derivative for scalar function pi xyt, if I take pi xyt, may be obtained, the total derivative for scalar function pi xyt may be obtained by considering total differential change total differential d pi is equals to dou pi by dou t into dt plus d pi by dou x into dx plus dou pi by dou y into dy. This field phi could be velocity component or pressure coefficient or temperature field, right? And now I want to derive it for a velocity component. Therefore, d pi by dt is equals to, I can write total derivative of d pi by dt is equals to dou pi by dou t into dt by dt is equals to 1. Therefore, dou pi by dou t, dou pi by dou x into dx by dt. This is equals to dx by dt, dou pi by dou y into dy by dt, and dy by dt is equals to v, and again dou x by dou t is equals to u. Therefore, this is equals to dou pi by dou t u dou pi. This is dou x by dou t is equals to u dou pi by dou x plus dou y by dou t is equals to v. Therefore, dou pi by dou y into v. This is equation number 3. I have noted down. This already we discussed and this, and total is, and now this total derivative d pi by dt, the what I have mentioned here. See, the total d pi by dt is total d pi by dt is equal to, it's resulted into dou pi by dou t plus u dou pi by dou u dou pi by dou x plus v dou pi by dou y. You have got it. Okay. Now for a steady state, condition, this is equals to 0. We'll write afterwards. Okay. First, before that, this equation is nothing but time rate change of pi, time time rate change of pi, and again this is called as a convective transport fields associated, right? Changes associated with convective transport field, and this is called as local rate of change. This is okay. Now for a steady state, I can say steady flow conditions. This and for steady flow condition, and for a two-dimensional case, this is equals to 0. Therefore, d pi by dt is equals to u dou pi by dou x plus v dou pi by dou y. This is the equation number 1. Now, for as I said, this pi is a function of x and y. For x direction, this pi is going to be replaced with for x direction, the velocity is going to be u. Therefore, the velocity I am writing it as du by dt is equals to u, and the pi is replaced with u, that is equals to dou u by dou x plus v dou u by dou y. This is one. And for y direction, the velocity component I am taking as v. Therefore, dv by dt is equals to u dou v by dou x plus v dou v by dou y is dou y. This I am denoting as 4c. Up to this we have discussed in the coming class, right? Now today we will be talking about body forces, right? We will be talking about body forces, right? Now, if we in body forces, if we designate x and y components of body forces are dx and dy. If we designate if we designate the x and y components of the body force per as a proportional to volume, as I said, therefore per unit volume, volume of a fluid as b suffix x and b suffix y respectively, then body force says acting on volume dx dy 1, the body force acting on element of dx dy volume in x direction in x direction is equals to body force bx into dx dy into 1. This is I am writing as 5 continuously. I am writing it as 5. Therefore, 4 I have finished. Now I am writing 5. And similarly, Similarly, body forces acting on dx dy into 1 in y direction is equals to by dx dy into 1. This is 5b. Right. Now I'm next, body forces and mass into acceleration is acceleration in j direction is equals to body forces, sum of the body force in j direction and plus sum of the surface force in j direction. Therefore, now I will talk about surface forces. Surface forces. Surface forces. At any point in a flow field, the stress system at any point in a flow field, the stress system generated by the surface forces may be resolved into two components. I'll write it. At any point in the fluid flow field, the stress system generated by the surface forces may be resolved into two perpendicular may be resolved into two perpendicular two perpendicular components two perpendicular components. One is normal stresses. First one is normal stresses acting normal stresses acting normal to the surface, normal stresses acting normal to the surface, perpendicular normal stresses acting perpendicular to the surface, and number two, shear stresses acting along the surface. Okay, to describe these stresses, now I have taken a elemental area dx dy in this fashion, right? In a Cartesian coordinate, this is dx and this is dy and this is xy. Starting point is now this is a surface, right? To this surface, normal stress is going to be sigma. It is I am denoting the stresses into two with a double subscript like this, y xx, the xy something like here I have mentioned it, xy and yx something like this. Okay, here what it says is what this stresses, right? The stresses I have mentioned, normal stresses and shear stresses are mentioned with a double subscripts. First subscript talks about this stress is perpendicular. This stress is first subscript talks about it is perpendicular to the axis, and it is in which direction it is acts. The second subscript talks about in which direction it acts. Okay. Now see here, this stress, it is like this is x direction, and it is perpendicular direction, therefore sigma, this is normal, this is denoted as sigma yy. Similarly, this surface, if I take it is normal to this surface, all right, this is dz is 1, right, and this is dy, to this perpendicular stress is going to be sigma xx, okay, right. So these are two normal stresses in x and y direction. Similarly, the normal stresses after dx, after crossing dx, could be sigma xx plus dou by dou x of sigma xx into dx. And similarly, in y direction, this is going to be sigma yy plus dou by dou y of sigma yy dy, and these are away from the element, right. These are tensions, right. This is tensile stresses, I can say these are tensile stresses, okay. Opposite, these are away from the axis. These are tensor. Similarly, and shear stresses, I am how to write. Shear stresses are, I am writing in this fashion. I'll start from here. This surface. This is equals to, I am mentioned as, this is towards that xy point. This is equals to xy point, and here tau y stands for, it is perpendicular to y direction, y axis, and it is the, and other one x stands for in the direction of x. It is perpendicular to y in the direction of x. I have written tau, right. Similarly, sorry. Similarly, if I go to other direction, see this is in the direction, it is against this opposite to this direction. Here, if you see here, this is tau yx, and it is in the x direction. I want to this is, see here, tau tau yx plus dou by dou y of tau yx dy, right. So this stress is at a distance of dy, how it is going to vary. Therefore, dou by dou y of tau yx dy, right. So this is in this y direction, right. Now, similarly, if I go to this other direction, this direction, if I see this one, tau xy means what? It is perpendicular to the shear stress is, the shear stress is here in this direction. In this direction means what? In the y direction, and it is perpendicular to x direction. Therefore, it is equal to x direction. Therefore, tau xy, and here in opposite direction after dx, it is going to be tau xy plus dou by dou x of tau xy and dx, right. This is one, okay. This is the description of the figure, right. Means what? The stresses due to surface forces dissolved into normal stresses and shear stresses. Normal stresses are which are normal to the surface, and shear stresses are nothing but along the surface. Along surface means the surface is available along x direction, and the surface is available y direction. Therefore, on x direction and y direction, I have shown shear stresses, and after that elemental the change of direction dx and dy also I have shown those diagrams. Okay. Now this is, once you know this one, now I will be going to discuss about the net force, net shear force. Now I am going to discuss about, once you know this, I'll going for a simple force balance, force balance in the x and y direction, y directions, that may lead to the following surface forces, right. I am going for a simple force balance in x and y direction. This may lead to simple forces like this. What is that? Nothing but net force. Net force means what? That is surface force. Net force is that is surface force acting in x direction is equals to, I will write it as, it is like this minus this, therefore sigma xx plus dou by dou x of sigma xx dx, right? Xx dx minus sigma xx, and area is dx dy. Okay, now this gets cancelled, this gets cancelled, and here dx, this is also dx is there, this also dx is there, and this is y, this is y, therefore this is equals to dou by dou x of sigma xx, right? Next, 1 minute, I'll write it. Net force acting in x direction, sorry, I'll write it thoroughly, right? This is right, sorry, this I net force is acting, I'll write it like this. Okay, now I'll write it totally here. Now see, this is, I will write it first, this normal stresses sigma xx plus dou by dou x of sigma xx dx minus sigma xx plus next one is x direction, this is x direction, this is equals to tau, this is away from it, therefore tau yx plus dou by dou y of tau yx dy minus tau yx into, this is stress, force is equals to stress into area, therefore area is going to be here, this is dy and this is 1, therefore dy into 1, then this gets cancelled, this gets cancelled. Now this is going to be the results is going to be here, I'll write it, that is equals to dou by dou x of sigma xx plus dou by dou y of tau yx into dx dy. This is equation number 6a, I'll write it. You just check it once again, I'll cross check it. This is one. See, this is dy, and this is okay. You can check it, right? This is equals to dy. Okay, dy. I can write this is dx here. Okay, so that's how you have got that equation. Okay, now this is one, right? Similarly, the net surface force, net surface force acting in y direction is equals to, I'll go here back, I'll write flower bracket. This is sigma yy, sigma yy plus dou by dou y of sigma yy into dy into normal area to this is dx into 1 plus next surface surface force, sorry, next shear stresses is equals to y direction is equals to y direction. What is this one? This one, okay. Tau xy, tau xy plus dou by dou x of tau xy into dx minus tau xy, and along is going to, along this axis is equals to, I'll write it along this axis, I'll show you. This is equals to, this is dx, right? This is dx into 1, therefore, sorry, y direction, sorry. This is right, this direction I am taking tau xy, and this I have written, therefore this is equals to dy, right? And then this is equals to, this gets cancelled, and here I have not mentioned minus tau yy, this gets cancelled. The equation is going to be dou by dou y of sigma yy plus dou by dou x of tau xy into dx dy. This is 6b, okay. 6b, okay. Now substituting equations 2, 4b, 5a and 6a into equation 1, we get the x momentum equation as equation as see 2 as, I'll write first, then I'll show you. Rho of u dou u by dou x plus v dou u by dou y is equals to body force in bx plus dou by dou x of sigma xx plus dou by dou y of tau yx. This one, okay. This is, I am writing as equation number 7. I'll show you this, okay. Now I'll first, second equation is, what is second equation is, you can see the second equation is mass dou rho into dx dy, that is mass here, okay. Acceleration, next equation is this, this is equal to, right, this is there, but this is converted into x direction is going to u dou u by dou x plus v dou u by dou x. So this is acceleration u dou u, this is written as 4b, right? Next, and 5a is this one, okay. And next 6a is this one. Substituting this, you will be going to get here dx dy, here also dx dy and dx dy. So everything is, if you substitute it, then this equation is going to be rho into this one. Mass is rho dx dy into a, this one, acceleration this one, and they're going to be gets cancelled this one. Okay, now this is 7th A, and similarly substitution of equations 2, 4c, 5b and 6b in equation 1, we get rho v dou u by rho v dou v, sorry, I'll write it here. We get rho of u dou v by dou x plus v dou v by dou y is equals to by plus dou by dou y of sigma yy plus dou by dou x of tau xy. This is 7th B. Okay. Now, right now, these equations are in generic nature. The solutions for the velocity field at various stages appearing on the right hand side. This one on the right hand, this here, this one and this one. Okay, right, this one and this one, right. So used for the solution of this various stresses acting on the right hand side, shilting has given 19 shilting SCI SCIL Shilting 1968 gave a equations for relative stresses for x and y direction, and this is like this: sigma xx is equals to minus p plus 2 mu dou u by dou x, the solution for stresses, normal stresses, dou u by dou x. This is 80A, and for normal stress in y direction is given by minus p plus 2 mu dou v by dou y. This is 8b, and for tau xy, which is nothing but tau yx, is also equals to tau yx is equals to mu into dou u by dou y plus dou v by dou x. This is 8c, right, where here mu, whatever here mentioned, mu is nothing but viscosity of the fluid. Mu is called viscosity of the fluid as viscosity of the fluid, right? Now if I substitute this equation 8 in 7a, this I denoting, this is a, this is 8a, and this is I am denoting as 9 instead of this one I am denoting as 9. Right, this is 8a and 8b. Substituting equations 8 and 9. Substituting 8 and 9. 9, then in dou by dou x of sigma xx plus dou by dou y of tau yx, we are going to get that is dou by dou x of sigma xx plus dou by dou y of tau yx is equals to dou here, dou by this one means what, minus dou p by dou x plus this one 2 mu dou square u by dou x square, right? Now this is 1, next plus tau dou by dou x or tau yx, dou by dou x, this one, okay, this is equals to mu into, I'll write it as this, mu into dou by dou y of tau yx, this is dou by dou y of dou u by dou y is equals to dou square u by dou y square plus dou square v by dou x dou y, right? That is equals to minus dou p by dou x, I am writing it as usual, plus mu into, I will be writing, this is 2 mu square is there, therefore I will write this is mu into dou square u by dou x square plus dou square u by dou y square, right? Plus here one more mu is there, this is equal to, again write, I am writing mu is into this is 2 mu dou square u by dou x, so therefore I can write here dou square dou, this I write it as mu into, okay, dou square u by dou x square, right? Plus here, see here again I am writing it is this I have taken it here, dou square v by dou x dou y is there, therefore dou by dou x I will take out, right? Instead of writing it here dou square v by dou x square, what I will do here, mu into dou by dou x I will take it out, therefore this is equal to dou u by dou x, already dou into dou u by dou x, dou square u by dou x square, it is coming, right? Plus dou v by dou y, right? That is equals to minus dou p by dou x plus mu into dou square u by dou x square plus dou square u by dou y square plus this is equals to mu into dou by dou x into 0. This is since dou u by dou x plus dou u by dou y is equals to 0 from the continuity equation, that is law of conservation of mass. Therefore this is turned equation, the equation is going to be dou by dou x into sigma xx plus dou by dou y of tau yx is equals to minus dou p by dou x plus mu into dou square u by dou x square plus dou square u by dou y square is the equation. We need to remember it. Okay, this is the equation we need to remember. Now this is similarly, this expression similarly dou by dou y of sigma yy plus dou by dou x of tau xy is equals to minus dou p by dou y plus mu into dou square v by dou y square plus dou square v by dou x dou square v by dou y square. This is dou x square. This is dou x square. Okay. Now, right? So this is about that one stresses on right hand side. Now substitute these are all. This I am writing as now. This once you have described this one, substitute this in equation. What is that equation number? Substitute this also in equation number. Uh, Equation number 7a. 7a. This is 7a. Therefore, that is equals to 7a. That means what? Rho into mu dou u by dou x plus v dou u by dou y is equals to bx minus dou p by dou x plus mu into dou square u by dou x square plus dou square u by dou y square. This is for x direction, and for y direction rho into v dou v by dou x plus this is u into dou v by dou x plus v into dou v by dou y is equals to by minus dou p by dou y of dou by dou y plus mu into dou square v by dou x square plus dou square v by dou y square. This is 10b. Okay, right? So this is 10b. This is similarly y momentum equation. This is x momentum equation and this is y momentum equation. Right? So means what? Rho of u dou u by dou x plus v dou u by dou y is equals to bx minus dou p by dou x plus u dou square u by dou x square plus dou square u by dou y square. This is x momentum equation, and rho of u dou v by dou x plus v plus v dou v by dou y is equals to by minus dou p by dou y plus mu into dou square v by dou x square plus dou square v by dou y square. This is y momentum equation. Okay, so this you need to remember these equations. Okay, now there is a physical significance here. This is inertial forces. This we called as a inertial forces. Left hand side inertial forces, and this is body force. Body force. This is pressure force. This is called as viscous force. Right? So the momentum equation is inertial forces is equals to body force, pressure forces, sum of body forces, pressure forces, and viscous forces. Right? This is something I wanted to talk about it. Right? And it is also written in the form of rho total derivative d v by dt, velocity dv by dt is equals to body force B minus del P, pressure force del P, plus mu del square u del square v. This is, I can write it in a other form where del square is called as Laplacian operators, is called Laplacian operator. Okay, right? So this is about the momentum equation. So the momentum equation, we need to remember this equation. I'll write it, I'll enclose it in a circle. This is very, very important to remember it. This one, rho of u dou u by dou x plus v dou u by dou y is equals to bx minus dou p by dou x plus mu into dou square u by dou x square plus dou square v by dou y square, dou square u by dou y square. This is very important to remember it. Okay. Now, so this, with this I am concluding this topic. I mean momentum equation. Now, if I start my energy equation, it takes lot of time to me to derive this equation. It may take more than 1 hour. So instead of stopping at the middle, what I will do is today I will talk about another topic called as dimensional analysis. It is also a part of your subject syllabus. So I will talk about dimensional analysis now. Right now, instead of this one, today I will be talking about dimensional analysis. Okay. Now, dimensional analysis. I am trying to complete this topic, dimensional analysis. More emphasis is on Buckingham Buckingham Pi theorem. Okay. So before going into this Buckingham Pi theorem, I will try to what is dimensions. All right, I will talk about it. Okay. As we have been studying that there are fundamentally there are 4 dimensions available to you. There are 4 dimensions. There are 4 dimensions. Okay. They are, first one is mass. It is denoted as capital M. Then length, it is denoted as capital L, and time is denoted as small t, and the fourth one is temperature. These are fundamentals, fundamental dimensions. These are 4: temperature, capital T. Okay. So these 4 are being used to derive other dimensions of the parameters like force, work, heat, specific heat, density, those things. Okay. Now, I'll try to cover some of some of physical quantities. I'll discuss now some of physical quantities and their dimensions now. Dimensions. This is very much required also to deal with the dimensional analysis cases. So I will be listing out some of physical quantities and their dimensions here. Right? I'll list one by one. First, I will write first serial number. I'll write it serial number and quantity, and symbol. How do you symbol? How do you show it? And the third one is the fourth one is dimensions. Right? This 4 rows I am taking it. We can write like this if you want. You can write like this. First one is quantized mass. As already shown to you, it is denoted as normally with the symbol M. and the dimension is going to be capital M. First, I'll write four fundamental dimensions. Okay. Next one is length. It is denoted as sometimes capital L, or sometimes it is denoted as X in heat transfer. The dimension of this is nothing but capital L. And the third one is time. It is denoted as small t, and dimensions is also small t. Next, serial number, quantity, quantity, symbol, and dimension. Okay, quantity, symbol, and dimension like this. Now, serial number, velocity. For this is address for velocity is, how do you define it? Is nothing but distance by time. Symbol is velocity is denoted by normally u, and distance by time. Distance is again the is nothing but a length unit, and dimension is going to be L only, and time is seconds. Therefore, I can write this is equals to L t to the power of -1. You can check it here. Velocity is equals to length by time or distance by time. This is L, and time is by t to the power of -1. Okay. Here I'll try to write one more is here temperature, the dimension temperature. You can show it is T, right? And you can write it as T to the T, capital T, right? Next, 6, 6 acceleration, acceleration, right? Velocity by time, this is equals to, therefore acceleration is denoted as capital small a, and the velocity by time, that is L t to the power of -1 minus plus -1, this is equal L to the power of -2, L t to the power of -2. Next, force, force is denoted as F, and this is equals to, force is written as MA. Mass into acceleration, mass dimension is capital M, and A you have no L into t to the power of -2, right? Similarly, work is denoted as F, and it is calculated as force into distance, force into distance, that is equals to, force is M L t to the power of -2 into distance, means for M L square t to the power of -2. Okay, and 8 energy as energy or heat, I can say. But work, and we know in thermodynamics we have discussed work and heat are two energy forms. Therefore, it is denoting directly, I am writing as this energy is E, or Q is nothing but the same unit of work, and again the same dimension it is having. Therefore, I can straight away write M L square t to the power of -2. Right now, 10th I'll write it. Work is over, energy is over. Now I'll write power. Power is equal to rate of doing work, or work done per second. Power is denoted as P, and it is work done per second. Work is equal to, L t to the L M L square t to the power of -2 by t to the t, that is equal to t to the power of -3 M L square t to the power of -3. Right? Now, 11th. 11th. density. Density is denoted by symbol is rho. This is mass by volume. Mass is m. Volume is length unit. Therefore, this is also length dimension. That is length unit. Therefore, L to the power of minus 3. Next, 12 pressure. Sorry, this is 12. This pressure. This is pressure. This is R pressure or stress. Right? Force per unit area is pressure or force per unit area is also stress. I can call it as. Okay. So now a force, force is this one by area is L square. Therefore, first I'll write the unit as P. I can use symbol is P or sigma. That is equal to force is M L to the power minus 2. For area is equal to L square. Therefore, M L to the power of minus 1 T to the power of minus 2. M L to the power of minus 1 T to the power of minus 2 force, right? And this is I can write force by area to remember it. Okay. Now 13. 13. Viscosity. Viscosity is denoted as mu. We know shear stress tau is equals to mu dou v by dou y, right? Or dv by dy, right? Now mu is equals to tau into dy by dv, that is tau shear stress. This shear stress, already stress, what is that stress you have got? M L to the power of minus 1 T to the power of minus 2 dv, velocity is L T to the power of minus 1 and L, this L cancel, this is equals to viscosity. Right. Dou y by dou v. Sorry, this is L T to the power of minus 1. This is not there. Right. This is equals to M L to the power minus 1 T to the power of minus 1. That is equals to M L to the power of minus 1 T to the power of minus 1. Right. And then kinematic viscosity, 14th. Kinematic viscosity. Viscosity is denoted mu, that is equal to mu by rho. Mu, M L to the power of minus 1 to the power of minus 1 by rho is M L to the power of minus 3, that is equal to M going to cancel and L square and T to the power of minus 1. Okay, this is one, and the next one I'll write it here. Instead of going to next page, I'll write it here. The next one is 15. 15. This is specific heat. Specific heat. The symbol I am denoting as C, and this is equal to L square T to the power of minus 2, capital T to the power of minus 1. How you can define is nothing but specific heat is equals to, what is the unit is kilojoule per kg. Kilojoule is nothing but unit of energy. Therefore, I'll write it here, kilojoule. If you want, I can show it here. This is I'll try to explain to you. This is equals to, specific heat is equals to, the unit is going to be kilojoule per kg, right? So kilojoule is unit of energy, that is equals to ml square T to the power of minus 2 kg is m is there, okay, by m, and temperature is T, therefore m gets cancelled, L square T to the power minus 2 and T to the power minus 1, right? That's how you have got it. Next 16th. Next, thermal conductivity. Thermal conductivity is equals to, it is denoted as K, right? This is also is denoted as M L T to the power of minus 3 T to the power of minus 1. The unit for this one is going to be thermal conductivity is watt per meter Kelvin. Watt is power unit. How come? So everything is erased, right? Now, anyway, we have at the end of this topic. Now, thermal conductivity. I have mentioned thermal conductivity. Thermal conductivity is denoted as K. This is equal to unit is watt per meter Kelvin. This is equal to M L T to the power of minus 3 and T to the power of minus 1, and thermal diffusivity. Thermal diffusivity. Thermal diffusivity, it is denoted as alpha is equals to L square T to the power of minus 1. I'll write it here. L square, our thermal diffusivity alpha is equals to K by rho C. K is thermal conductivity, I have written as M L T to the power of minus 3 into capital T to the power of minus 1, capital T to the power minus 1 divided by rho. Density, you know, density is the information is not available to me. This is equal to M L to the power of minus 3, and C specific heat is given as L square T to the power of minus 2 and T to the power of minus 1. So this gets cancelled. This L square is L to the power of minus 1, and this is so C is L square, right? So under T to the power of minus 2, because minus 1, this, so T to the power minus 1, you are going to get T to the power of minus 1, L gets cancelled, and this is equals to L, this is equals to L to the power minus 1, and if it goes to here plus 1, L 1 plus 1, this is L square T to the power of minus 1 you have got here, okay? Thermal diffusivity, right? Next, heat transfer coefficient. Heat transfer coefficient. This is denoted as H. The unit for heat transfer coefficient is nothing but watt per meter square Kelvin. Watt is the power, unit of power. Unit of power, you know, that is equal to your power definition, power dimension m L square t to the power of minus 3 meter square is unit length L square, and Kelvin is t to the power of minus 1. Sorry, Kelvin is t. Therefore, this is equal to L gets cancelled, L square gets cancelled, m is there, t to the power minus 3 is there, and t to the power of minus 1 is there. Therefore, m t to the power of minus 3 and t to the power of minus 1. Okay, heat transfer coefficient and coefficient of thermal expansion. Coefficient of thermal expansion is denoted as beta. This is equal to t to the power of minus 1. Alright, this is something, a coefficient of thermal expansion is t to the power of minus 1. Okay, these are the dimensions for some of the quantities or parameters, like which are come across in case of a convection problems. Okay, now with this I am going to write Buckingham Pi theorem. I will be writing Buckingham Pi theorem and I will try to discuss about this. Right, now I will be writing Buckingham Pi theorem. Now, so, right, this theorem is used as a thumb rule for determining the number of independent dimensionless groups that can be obtained from a set of variables. This theorem can be used as a thumb rule. I'll repeat it again. This Buckingham Pi theorem can be used as a thumb rule for determining the number of independent dimensionless groups that can be obtained from a set of variables. Okay, from a set of variables. Right. So Buckingham Pi theorem. I'll define this one. Otherwise, the Buckingham theorem, how it's framed, I will try to talk about it here. All right. For example, let A1, A2, A3, etc. up to A1. Sorry, I will write it totally. Let A1, A2, A3, A4, A5, A6, A4, A5, and A6 be the relevant variables in a problem and let these 6 variables be expressed in terms of four basic dimensions. They are M, L, small t time, and again capital T. Okay, let there are A1, A2, A3, A6, A3, A1, A2, A3, A4, A5, and A6 be the relevant variables in a given column, and these are six variables, right? I mean to say there are variables, and these variables have can be expressed in terms of four basic dimensions. These variables can be expressed in four dimensions: M, L, T, and T. Then the number of I will write it. The number of independent independent dimensionless groups representing this phenomena would be would be would be according to Buckingham Pi Theorem. Buckingham Pi Theorem is 6 minus 4 is equals to 2. Means what? If there are six independent variables and these six independent variables may be expressed into four dimensional groups, then 6 minus 4 would be 2. This can be expressed into two dimensional groups. That is the meaning of it. Okay, two dimensional groups. Thus, two dimensional groups I am naming as phi 1 and phi 2. So that is expressed as f is function of phi 1 and phi 2 is equals to 0. This is something like you need to remember it. Okay. Now this is Buckingham theorem. Means what? It may be used as a thumb rule. This theorem might be used as a thumb rule for determining number of dimensionless groups that can be obtained from a set of variables. Set of variables are this like A1, A2, A3, A4, A5, and A6. Okay. This can be expressed, this A1, A2, these variables can be expressed into the form of in the basic dimensions like M, L, T, and capital T, M, L, small t, and capital T. These are four basic dimensions. Therefore, these are four basic dimensions, and there are six variables. Therefore, variables minus basic dimensions is equals to the number of dimensional groups that can be formed out of this given. Therefore, this is something like you need to remember it, right? Now, so with this, I am trying to write dimensional analysis applied to forced convection. With this small introduction, I am going for dimensional analysis for forced convection. Okay, to analysis this forced convection, let us now consider now consider the case. Okay, let us now consider the case of a fluid flowing across let us consider the case of fluid flowing across a heated tube right. When the fluid flowing across a heated tube, The variables to be considered are, now I'll write variable and their symbol and dimensions. The variable considered are variables, independent variables, rather like variables considered and symbol and dimensions. Okay, variables first, that heated tube, therefore the tube diameter I want to know, right? Tube diameter, tube diameter, or I can say this characteristic length of tube, characteristic length, symbol is diameter D, and unit is L, dimension is L, and number two variable is going to be density, fluid density is denoted by rho, and density already you know, mass by volume m L to the power of minus 3, and fluid viscosity, fluid viscosity is denoted by mu, that is equal to m L to the power of minus 1 to the power of minus 1. Already I gave you all the information. And fluid velocity, fluid velocity is u, that is L t to the power of minus 1 L t to the power of minus 1, and 5 specific heat, specific heat Cp is equal to L square t to the power of minus 2 on t to the power of minus 1, and 6 thermal conductivity, thermal conductivity, it is, the symbol is small k, and this is m L t to the power of minus 3, and ml t to the power of minus 3, capital T to the power of minus 1, and 7 heat transfer coefficient, heat transfer coefficient is h m t to the power of minus 3 t to the power of minus 1. Okay, means there are 1 2 3 4 5 6 7 variables, 7 variables, 7, and they all variables are being shown as how many dimensions. L is there, M is there 2, and T is also there, and capital T is there. It is shown as dimensions are 4 dimensions, basic dimensions are 4 dimensions, 4. Therefore, number of independent dimensional groups, dimensionless, therefore number of dimensionless groups is equals to 7 minus 4 is equals to 3. They are expressed as function of pi 1, pi 2, and pi 3 is equals to 0. Right? Now, as per we know that. Right? Now, I'll be writing pi first one. Pi 1 is equals to, first Pi 1 is equals to, I'll write Pi 1 is equals to, see, I'll try to combine, here I am going here, I'll write it here, I'll explain to you, D I am writing it as D rho mu and K I will take, D rho mu and K I take, right? So I'll write it as D to the power of A rho to the power of B and mu to the power of C, K to the power of D, and the other one which I has not considered here, which has not D I have considered, rho I have considered, mu I have considered, K I have not considered. Which I has not considered is U, CP and K. So in pi 1 I use mu, and in pi 2 I use CP, and pi 3 I use H. Therefore here what I will do is I will use U, right? So this is pi 1, and similarly pi 2 I use the same. D is common, right? These are common variables. Therefore, D, but superscript I am using E exponent D to the power of E, rho to the power of F, mu to the power of G, K to the power of I, and Cp. Okay. Similarly, for pi 3, I'll use D to the power of G and rho to the power of L, mu to the power of M, K to the power of N, and H. See, what I have discussed is, first I have used mu for pi 1, CP is for pi 2, and H is for pi 3, right? So this is something, the idea I am giving it to you. And pi 1 is going to be dimensionless number, means that I will write it, right? First one I will write M0, L0, T0, T0 is equals to 1 is equals to dimension of diameter is L to the power of A, rho is density, this is equals to, alright, mass by volume M to the power M by L cube to the power of B, and mu M by LT to the power of C, and K M L by T cube T to the power of D, and U is L by T, right? So what I did is nothing but I wrote this symbols, means what, this para variables D, rho, mu, K, and U in terms of dimensions. Okay, in terms of dimensions. So I wrote here in terms of dimensions. I am equating both sides of superscripts of M, L, T, capital T on both sides. Therefore, I will equate M. For M, I am equating for M. For M, left side is, it is 0. Right side is M to the power of B. Therefore, M to the power of B. Therefore, M bases are same. Therefore, I'll add the exponent. Therefore, B plus M to the power of C. Therefore, C, M to the power of D. Therefore, D. This is 1. Okay. Similarly, for L, it is 0. This is equals to A L to the power of A, and minus 3B is there. This is equals to L to the power of minus 1 into C, minus C, and L to the power of D plus D L is there here, 1, nothing is mentioned, is 1, L to the power of 1. Similarly, for a small t is 0, okay, and it is t, it is going to be minus c minus 3d minus, this is small t, right? L by t. U is L by t, small t. T minus 1. Okay. And for t capital T, this is 0. This is equals to minus, here no t is there. Capital T, here t is there. Therefore minus d. Right? Therefore d is equals to 0. And so if we substitute d here 0, this is equal to 0, minus c minus 1 is equal to 0. Therefore c is equals to minus 1. C is equals to minus 1. And D and C substitute here. D is 0, C is minus 1, B is equals to 1. Similarly, B, C, D are substituting here. B is 1 minus 3, C is equals to minus 1 plus 1 is this, right? Minus 3 plus 1, this will minus 2 and plus 1, therefore 1. Therefore, A is equals to 1. Okay, therefore pi 1 would be d to the power of a. D to the power of a, L to the power of a means what? Pi 1 would be d to the power of a. It means that a is equals to 1. Therefore d is there, and rho to the power of b. B is equals to 1. Rho is also there, and mu to the power of c. C is equals to minus 1. Therefore minus mu, right? And next k to the power of d. D is 0, therefore k to the power of 0 is equals to 1. And u to the u is also there, u. Therefore this is equals to rho u d by mu is for pi 1. Similarly, for pi 2 is equals to, the same way if you follow the pi 2 is equals to, you are going to get is mu cp by k. This you can write it as PR, you can write it as, and this pi 1 is equals to, you can write pi 1 is equals to R, Reynolds number R, RED. Alright, and pi 3, from this pi 3 you can write as pi 3 is equals to, solving this one you are going to get, let me check this pi 3. Pi 3 is equals to HD by K. You are going to get HD by K is equals to Nusselt number N. Therefore, we may express F is a function of F1, F2, F3 is equals to 0, as we can write it as Nusselt number is equals to pi of, this is pi 3 is equals to pi 1 is RE, and again this is called as a PR. This is equation number 1, right? Here it is, we can also write it as standard number is equals to Nu by Re into PR. That is equals to Nu by R into PR is nothing but Nu is HD by K. Re is, I can say Re is here rho ud by mu, and the PR is mu Cp by K. So K gets cancelled, mu gets cancelled, D gets cancelled. This is equals to H by rho CPU, row CPU. This is standard number. I can remember it. So right. So here this is, I can write a standard number is also a dimensionless number. It is going to be a nu by REPR, a nu by REPR. Therefore, I can write I can write standard number is equals to standard number n is equals to pi into pi REPR. I can write it. Okay, this is something like I want to mention here. Okay, so this I'll talk about in thoroughly in coming class. So dimensional analysis is used to group into dimensional analysis used to group independent variables into some dimensionless groups. That is the meaning of meaning the you can get at the initial stages. Now after coming to the next class, I will try to talk about the natural convention. In that, we will talk about some more details about it. Okay. So now I will be stopping here. In the coming class, we will talk about some more discussions. Okay. Right. Thank you.